Hello, hello. Thank you all for jumping in and learning about zkTLS. It's an exciting topic. My name is Ryan, and I'm the founder of Usher Labs. At Usher Labs, we've been doing a lot of research into data verification and data storage. I think the last year we did a lot of work on zkTLS because we realized how important this technology could be. And so the quest was, how do we build out a framework to support data flows, tamper-proof data flows, so that we can build private and fast blockchain oracles. And of course, that's powered by zkTLS. But before I dive into that, a little about us, myself. I've had experience at payment startups in Australia, some publicly listed ones, and founded this company alongside a bunch of data engineers, essentially, that all have some prior experience in Web3 or were totally new. And some of the companies we've served were mostly use cases with zkTLS or somewhat touched on data in the past. But the quest has sort of led us to our own use case ultimately, which is in DeFi. So we sort of realized, okay, why we have zkTLS work, let's just apply it. And so this talk is going to be revolving around that, how we're applying zkTLS to our use case. But I'll get to that use case at the end. Let's talk about Verity. Verity, this framework. Why does it matter, right? Institutions, from our perspective, hold all user private data. There's a lot of zkTLS solutions that go for, the browser extension approach. We focused on the APIs, right? Getting permission from Plaid, for example, so you can tap open banking APIs. So a high-frequency server-side indexing of real-world data from institutions was the mission. You can think of this like extract, transform, load, except with verifiability. And the result through this framework is to allow blockchains to say, what happened to this data in the past so that we can do stuff with it, right? Is the data correct? Where did it come from? Are these conditions met? So ETL is the mission. Now, I've prepared some demo. I can skim through a little bit of this. Who here is a programmer, by the way? Okay, perfect. So you've worked with a terminal. Yeah, a little bit of a tech-heavy demo today. But this is just a small introduction to how Verity works. It's a simplification of engaging TLSNotary. It uses CLIs to engage, the prover and notary, and of course, verification of proofs. But what we've done differently is with our prover, it acts as a proxy. And immediately, the first thing we do is set up sort of a subscription to a proof. And we use a request ID to correlate this async proof to a request for a proof. So you can run this prover proxy as a, for example, microservice from whatever backend you're operating, and it does TLSNotary for you. Now, we're using the latest version of TLSNotary, so shout out to Buenos Labs and the TLSNotary team for that heavy lift, because it's actually insane. Very fast. And you can see I've just copied the proof, no server-side event metadata into a file, and using CLI, we verify and get Bitcoin price. Pretty simple. But let's move on. For the sake of time, I can show you what redactions look like, but I think it's pretty straightforward, and we have public docs for that. I'm going to focus a bit more on like the innovations from our end, like what do we do to TLSNotary that actually is new. We like to call this first thing preparation and concurrency. And the quest here was like, how do we reduce the time it takes to generate a proof? How do we minimize the time to proof, if that was our KPI? And so in this first demo I'm going to show you is actually an attempt using TLSNotary's example for concurrent proof generation. And so here you see, some code. The code is, what it's doing is actually a batch of 4 proofs done concurrently, but staggered 1 second apart to JSON placeholder, website. And so basically 4 proofs at a time, they happen 1 second apart, and it happens over and over again. So how do we get 4 proofs at a time, basically? And so when I run this, eventually, yes, I added some, I started the benchmarks after the prover and notary setup to give some leeway to the TLSNotary example. But when I run this, yes, starts working. Okay. And you see the average time to proof by the TLSNotary example is roughly about 1.5 seconds for this specific API request. And of course, depending on the size of the request, it's going to vary, time to proof. but using this local environment, the average is 1.5 using default. Let's move on. Okay, cool. Now, let's run this demo. This demo is essentially what Verity can do. By incorporating this paradigm of preparation and concurrency, and by knowing which endpoints we want to reach before we actually execute the proof for that particular endpoint, the outcome we actually get with Verity is, oh, sorry, this is wrong demo. Okay. Let me try to zoom in. Okay. Skip in. Okay, cool. So I'm just going to pause there and describe it. So the first part of the demo, what I did is I ran Verity without any awareness of what happened prior, right? No awareness of which domain I'm going to reach. And by default, because Verity is a microservice-based tool, there's a little bit more overhead than the default TLSNotary. So every request that's being received is unknown to where the destination is. TLSNotary is cool. But the meat of this innovation comes from when you know where you're going to be making requests. And the objective is that, like, if you're indexing data from Binance, if you're indexing data from CoinGecko, that you're aware of these domains, and therefore you can prepare for those domains in advance of executing the proof. And the outcome of this is, I'm going to demonstrate that now, is that we set up this prover with awareness of this particular placeholder endpoint that we tested against the default TLSNotary. And when I run it, the average proof time is 0.5 seconds, right? So from 1.5 seconds to 0.5 seconds, simply by knowing in advance what the destination endpoint is. And so for anybody who's indexing the world using zkTLS and doing it in high frequency, I implore you to check out the framework. It's mostly open source, so we're openly sharing this information because we're moving mostly into applying this in DeFi, and know that there's a lot of zkTLS innovation that could leverage this. Okay, let's see what's going on here. Okay, let's move on to the next innovation. So the first one was decreasing time to proof. And the second innovation here is how do we actually roll all of these TLS proofs up? Like in our circumstance, we're going to be generating like 10 different proofs for 10 different, Binance accounts, for example, or we can take 10 proofs from 10 different centralized exchanges and produce one proof of reserves. How do we do this? Well, we want to roll it up, right? And to roll it up, shout out to Michael from Brevis who detailed using the recursive approach. We need a zkVM to roll up, or some decentralized compute as an alternative. If we can allow for data to be public. But let's assume we want to focus on private data because that's where the meat is. We need a zkVM. Well, zkVMs can actually be quite expensive in operation if there's a lot going on that doesn't necessarily need to be there. And in our perspective, TLS proofs by TLSNotary are actually comprised of 3 sub-proofs. The first is the attestation, the identity, the second is identity, and then the third is transcript. And the transcript is really where all the private data sits. It's whatever gets sent and received from the server. The identity is where you hit, right? That can be considered private, but if you're verifying things on chain and the conditions predicated on where the data came from, that can be public. And then of course the attestation is a signature and a Merkle root that ties everything together in the proof. So our objective here is like, how do we actually destructure the TLS proof so that we can take the private stuff and put it in a zkVM, generate a zk proof, and then correlate that to some public stuff that was in the original proofs and the zk proof. And then what we get as an outcome, essentially, is like a zkRollup of a bunch of data that we got from the internet. End-to-end verifiability with closing out that goal of extract, transform, and load. Because we're incorporating the compute side of things, that transformation allows us to, for example, run compute on data that was private. But yeah, this is an alternative architecture. This is the original. This is the one we're using, right? ZK proof and public stuff goes together to a public network that verifies it all together. We use the internet computer because it's cool and it allows us to do compute and generate an MPC SIG of what was done. But you can, incorporate your own ZK VM or use your own decentralized compute. Yeah. So I'm going to show a final demo here. And this demo is mostly around just showing you an example of the zkTLS flow in action. And so if you take a look at this code very quickly, if I pause it so we can read it, it's quite straightforward. We make a request using Verity TLS prover, and then we run it inside of a ZK VM. We verify the private facets inside of a ZK VM, and then we take that and the public stuff and put it on a decentralized compute to roll it all together. Now, I try eventually. Yeah, okay. Still looking at code. Okay, cool. So I go ahead here and I actually try to generate the ZK proof. And if I sat here and actually ran through the ZK VM proof generation process, you would probably be end of the day. So what I do instead here is I actually just comment out the ZK proof generation, because ZK proofs require GPUs, right, in real life. So yeah, I mean, GPUs are provided by many of the ZK, proving networks. They're all using GPUs to generate your ZK proofs. So yeah, what I do instead is I use a fixture. It's a saved ZK proof instead to demonstrate that, we've generated this proof in the past and we're verifying it alongside the other TLS proof sub-proofs. Yeah, so that's the outcome here. After we verified everything, we see that we made a request to a domain called mock.verity.usher.so. So you see, it sort of works, and we get a signature too of the outcome. Okay, let's start to wrap things up. So the use case that we're applying this for is to actually expand the depth of a market on a DEX like Uniswap. How do we, allow for fiat in a bank account, for example, to back the depth of a stable coin in the same, that represents the same fiat? The outcome of doing that is, we have a lot of depth, low spreads for markets like USDC to peso coin. No one wants to lock up their peso coin, but there's a lot of peso in bank accounts. So why, let's make DEXs aware of all that fiat is the mission here for us. But other case studies we've actually presented is, for example, reducing the cost of accessing data from a network like Internet Computer. They have their own internal Oracle mechanics. By using zkTLS, we actually reduce the cycle consumption on their network by 90%. And we've shared that in a forum post, where in the comments you can see me go back to back with one of their community members. That's an example of just the cost reductions of generating a proof on one node instead of having a whole network request the same endpoint. We also presented the graph over in Zurich regarding this to their team, how there's a bit of a trade-off where if you're requesting more data, 10 requests per minute, for example, it's a lot more efficient to use zkTLS. The last thing I want to open up the stage for, I mentioned earlier, this is a research project, so we're open to collaboration. If you're looking for, smaller time to proof, or you're looking to roll up a bunch of TLS attestations, we're down to collab. But the final thing that's a bit of an open roadmap I think we should all consider is this concept of collusion. And in my opinion, humbly speaking, I think cloud provider enforced TEEs are underrated. I think that if you take the notary and you isolate specific functions around key generation and startup and so on inside of the TEE, and you include a TEE attestation inside of the TLS proof itself that indicates where the signer came from, using TLSN extensions, then I think we can really solve this concept of collusion, because we shift that trust over to the cloud provider as opposed to trusting a network of notaries or something like this. So yeah, here are my contact information. Feel free to reach out, and Hopefully you guys followed, but this was quite technical, so if you did, I give you a pat on the back. Thanks.